There is a nice formula for you. The expectation. What would you expect to happen? So if we have our probability distribution, and we look at everything that's happened, what would you expect to happen? If you rolled, or if you flipped a coin 3 times, how many heads would you expect to get? And this is an interesting question because you would say to yourself, there's a 50% chance of getting heads, right? So if I flip a coin 3 times, how many heads should I get? 2 or 1 or 1.5? 1.5 times. Okay? Now, you can't have it happen 1.5 times, but that would be the expectation. And so you would use that expectation, meaning that if you had done the experiment more often, you could get an idea of what would happen. So the expected value is like the mean of a random variable, and it's the average value that you should expect if you did it over many, many trials. So it's not only based on what you're expecting, the values, but also on the probability associated with each value. So let's see what that means. If we had this, for the random variable, and I'm going to change this just so it feels better, to a 3. What does this mean? Okay? Well, one way to think about this, since each of these have a 1 out of 10, something out of 10 chance, does it make sense if you conducted this experiment 10 times that you would expect to get a 1 once, a 2 twice, a 3 times, and a 4 3 times, oops, there we go, a 3 times, and a 4 times? Does this give me a probability of getting the 1 out of 10, probability of getting the 2 out of 10, probability of getting 3 out of 10, and 4 out of 10? So if we consider this, how would you find your average? If those were the 10 possibilities, and you wanted to find the actual arithmetic mean, you could add them all up and divide by 10. So if we divided them all up, 12 plus 9 is 21, plus 4 is 25, 26. Our mean is 2.6. So our expected value, we'll find out, is going to be 2.6. The median is the one that happens right in the middle. Where does the median happen here? Between 3 and 3, right? Right, because there's 10 terms, so it's going to be the average between the 5th and the 6th one. So our median is equal to 3. And of course, which one happens the most is 4. So one of the things you can do with a probability distribution is once you look at the probabilities, you could say, if this happened, in this case, since the common denominator is 10, if this happened 10 times, this would be my theoretical result. 1 1, 2 2s, 3 3s, and 4 4s. Yes? That's equal to 30? Okay. I forgot to add 1 in the 4s. Thank you. There we go. So our mean is 3. Okay? And we would have discovered this error in a second, because the next thing that we're going to look at is our expected value. And the way an expected value occurs is you look at the event. The first event is a 1, and say, what are your chances of getting that? 1 out of 10. Plus your second event is a 2. What are your chances of that? 2 out of 10. Plus 3 times 3 out of 10, and 4 times 4 out of 10. This will give me 1 out of 10 plus 4 out of 10 plus 9 out of 10 plus 16 out of 10. And if I add these up correctly this time, I'll get 30 out of 10, which simplifies to 3. So if we go back to our previous screen and look at the formula for expectation, okay, it says it's a sum of each value times by its probability. And it's really the exact same formula that you've always used for mean, right? You just add up how many you have and divide by how many there are in total. But the probability already has that built into it. So if we look at our results from this question that we just completed, can you see when we listed it out 10 times and had 1, 1, 2, 2s, 3, 3s, 4, 4s, and added it up correctly to 30, that our mean would be 30 divided by 10 things 3. When we do it as an expectation formula, we have the 1 happens 1/10 of the time, the 2 happens 2/10 of the time, 3 3/10, and 4 4/10. And you can see that your numerators are adding up to the 30 just like before, but you already had the total built in. So where this is really nice is when you don't have something that lends itself well, like the probabilities don't lend themselves well to listing them all out, right? If some of these probabilities were like 37%, as a fraction you'd have to write 37 out of 100. You'd have to write that item out 37 times, which would be kind of annoying. And so our expectation is the same as our mean. So now, gut feeling. You roll a dice. On average, what do you roll? What's your gut feeling? 3.5? Seems reasonable. I mean, you can't roll a 3.5, but half the time you should roll 1 to 3, something below 3.5, and half the time above 3.5. So if we drew our probability distribution, okay, the random variable denotes the number showing. So here we have x could be 0, 1, not 0, sorry. So used to starting with 0. 1, you could get a 2, a 3, a 4, a 5, or a 6. And the probability of each of these are the same. So our expected value is going to be 1 times 1/6, plus 2 times 1/6, plus 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. which ends up being 21 over 6, which you're correct, works out perfectly to 3.5. So example 3, we want to find the expected value. Again, take each value, use the number and the probability. Does that add up right? So if you would actually like to reenact this experiment, so this is some experiment where you can get a 0, a 1, a 2, or a 3. If you wanted to reenact it, you'd have to make each of these out of 30. The 0 happens 5 times, a 1 happens 15 times, a 2 happens 6 times, and a 3 happens 4 times. Do a quick check. Does that add up to 30 out of 30? Yes. And if you wrote out a 0 5 times, a 1 15 times, a 2 6 times, and a 3 4 times, added them all up and divided by 30, you get 39 out of 30.